Thank you very much. Muchas gracias. Grazie. First of all, I wish to really thank the organizing committee for wanting me here in Bahia Blanca. It's a great chance also to work with people here at CONICET. And I wish to thank in particular Emma Casanave for the support. Thank you. And Mauro Lucherini for organizing everything here, and many, many friends that I'm making here that are supporting the work here. So today I will present you with a general overview of the conservation status of mammals, the future perspectives for mammals, some lessons that we learned from the recent past on the conservation of mammals. You're all very much familiar with this picture, but I always introduce any of my talks with this picture. That's the growth of the human population in the Holocene, the last 8,000 years, when the world has become dominated by humans. It's also called the Anthropocene for this reason. And you can see from this that the human population has always been much, much less than 1 billion people for the entire history of Earth, until 300 years ago, the Industrial Revolution that has changed everything, has changed the world and has changed everything for our natural environment. Population has exploded, human population has exploded to 7.5 billion in 2017, and despite projections of population growth slowly decreasing in the next decades, we still don't see this happening. This is why this era is called the Anthropocene. This is the island of Malé. It's the capital of Maldives. If you want to go and have a rest somewhere and have a nice time on the beach, make sure you choose carefully which island you go to. That's one example of transforming natural environments into human-dominated landscapes. You're fortunate here. You still have a lot of wild or semi-wild places. You also have a lot of places that are not much populated but very much transformed, so you know exactly what it means anyway. Even if Argentina is not built up this way entirely, it is heavily transformed anyway, at least part of it. And the founder of conservation biology, Michael Soulet, who my colleague and friend Kevin Crooks here knows very well personally, postulated in 1991 that if human population grows so much, this has to have consequences for other species. That's from a very classic paper in Science by Michael Soulet. And at the time, it was not such a trivial prediction. And he had to sketch it using a pen because he didn't have the data to support this idea. Now we have the data to support the idea, and I will show you some of the data. This is a map of global wilderness. That's a work by James Watson at University of Queensland with several of his colleagues. I'm not part of it, so if you want to complain for the lack of wilderness areas in Argentina, go to James and tell him it's not me. But this map shows that even in the last 16 years, there have been substantial losses in the wild places in the world. So the global wilderness has been reduced even in the last 15 years in remarkably in certain places. Look at the Amazon basin, how much has been lost in terms of wild area. Wild areas means vast expanses of land that is not transformed. And this trend is continuing. And this is just a hook for Kevin's closing plenary at the end of the week. That's another way of looking at the effect of global transformations of habitat, global anthropization, This is a map of habitat fragmentation for mammals, global map that Kevin has developed over the last few years and that we published in PNAS earlier this year. And it shows that in several places, and I would say in almost all places that are not desert here, desert here, desert here, or semi-desert, or very vastly unpopulated, and with the only remarkable exception of the Amazon basin still, most of the rest of the mammalian habitat is highly fragmented. So that's another visual clue of what is the impact of humans on species and on mammals in particular. And now, decades after Michael Soulet's prediction, we have data to feed the same information that Michael wanted to convey in his sketched figure. This is the red list index for all groups that have been assessed, that had been assessed by year 2010. That included amphibians, mammals, birds, and corals that had been assessed more than once because the red list index calculates the extent to which species moves towards extinction or they move away from extinction from time to time. So what you can see is that all groups are sliding down towards extinction. We are talking about mammals here, but I just want to flag corals because when we came up with this picture here, I dubbed it. I didn't believe that corals were going down so fast. Now with extensive coral bleaching and the loss of a big portion of the Great Barrier Reef in Australia, we know that this trend was real, and the forecast, the short-term forecast that one could do based on the red list index was correct. So beware of the red list index, it might be right. On the right, you see the same thing for mammals, not just mammals, but large mammals, large-ish mammals, let's say, carnivores and ungulates, smaller carnivores and larger carnivores, smaller ungulates and larger ungulates, all going down towards extinction. So their conservation status is worsening over time. And in this case, we backcasted the conservation status of species to 1975. That means that we use the information that was available at the time to make the red listing of the species in the past. And the situation of all species was much better than it is now. And I will show you in a while the update to 2017. So overall, about 1/4 of the species are at risk of extinction. This again, is a summary of what we knew in 2010. Now we know a little more, but the global picture hasn't changed very much. In different groups, you have the proportion of species that are threatened with extinction, which means yellow, orange, red, 3 levels of threat. We will talk about that in the lecture on IUCN Red List. But take it for granted that the yellow, orange, red is threatened species. The gray is data deficient species, species for which we have not enough information to assess the extinction risk. Green is species that are either least concerned or near threatened, so not an immediate threat of extinction. And across all species, the average is 1/4 is threatened with extinction. So given this general picture for biodiversity, what is the conservation status of mammals now? So first of all, we have more mammals than we had in 2008. And this is not, of course, true, but we know more about mammal taxonomy. So the IUCN database for mammals now contains more than 6,000 species. There were 5,500 in 2008. So that's almost a 10% increase in 10 years. And as you can see, of course, the most spacious groups had the most increases. They contain the most new species. The ones under review means that they are not yet published on the IUCN Red List, but we know that those species are there, so they will be eventually in a short while. Rodents, bats, we have a lot of new species here, and we have a lot of new species among primates as well. That's, of course, mostly genetic work. It's not finding new monkeys around the world. It's splitting species that were considered a single species in the past and are not anymore right now. And right now we have reassessed 2/3 of the species, and we have in reality, and they are already published on the Red List. They have a date post 2008, and in reality we have reassessed more. We are above 5,000 species out of 6,000. Those in progress, again, we know what the category is, but it's not yet. It's like in press, and we're still making small changes to the assessments, but not to the substance of the categorization of extinction risk. So we are at about 85% of the species. So the picture that we have now is an almost complete update, or let's say a reasonably complete update over 2008, and we know what has changed more or less. There will be some surprises in the remaining 14%, but not many. Not very, in the remaining 16%, but not very many. Just to give you some news for Argentina, 73% of the species, so more than 66%, the blue bar for Argentina would be larger here, have an asset of the species, mammal species that occur in Argentina, have been reassessed after 2008. There is 100 species missing, and these 100 species is mostly rodents, a few bats. There are 6 monkeys that are in progress, I know, and will come soon. But all of them will come soon because the specialist groups that are dealing with these reassessments are working actively and producing the assessments that are still missing. So what has changed since 2008? Mammals are slightly more threatened than they were before. The best estimate was below 25% in 2008, and it's now above 26% in 2017, with a range of the estimate that goes between 22.4 to 37.7%, and this wide range depends on data deficient species. If all data deficient species were threatened, we would come up with an almost 40% of mammals threatened with extinction. But we know that this is not the case. This best estimate simply considers that the proportion of species that are threatened among the data deficient is the same as among the data sufficient. So if this is the case, then more than 1/4 of the mammals are threatened with extinction right now. The figure is much lower for Argentina, as you can see. It's less than half than the global figure. Of course, this is not the country-level assessments that you're doing now. This is the global status of mammals that are that occur in Argentina. So they can be much more threatened in Argentina, or even less threatened. We will talk about that afterwards, after the plenary. Could be even less threatened here for because they're better conserved. Conservation status by order. Again, of course, the largest number of threatened species in absolute terms is found among the orders with more species. The proportions, if we look at the proportions, that's the proportion of threatened species, and the blue line, the blue dotted line, is the average, the 26.4%. We see that there are certain groups that are highly threatened. Pangolins are all threatened with extinction. And this is a big change in comparison to 2008, partly due to more work done on the conservation status of pangolins after the establishment of a specialist group that is devoted to pangolins only. elephants, of course, sirens, horses, and primates are all very much threatened with extinction, as well as monotremes. And then there are other groups that are slightly above average or slightly below average. But these are the highlights of entire orders being either entirely threatened with extinction or having the vast majority of the species threatened with extinction. In terms of number of changes since 2008, we had 73 deteriorations in conservation status and just 14 improvements. And the iconic species that you have here are actually representing disparate cases of conservation going really bad. Now, actually not just the orangutan, but all great apes are threatened with extinction except us. This is something that always blows my mind when I think about it. On the other hand, pandas are less threatened than they were before. This is no news now. This was in the press a year ago when the assessment came out. But it's still an interesting story, and it's a story of great conservation effort by the Chinese government that actually invested a lot in pandas, and the population of pandas has been steadily growing over time for more than a decade. And now the panda is not anymore endangered, it's vulnerable, which means that it's still threatened with extinction, but less than before. And if you look at the genuine status changes since 2008, maybe a word on what I mean by genuines. And actually, when I say 73 deteriorations and 14 improvements, I'm talking about genuine changes in the red list. There are many more changes than these, but several of them depend on, for example, improved knowledge on the status of the species. So a species that was considered to be in one threat category in 2008, now it's considered in a different category, but it's not a real change in status. It's just that we know more and we can make better assessments of the extinction risk. But the changes that I'm talking about here are all genuine changes, so populations having gone up or down. Among the unconfirmed data, we have a lot more changes, so deteriorations could be up to 140 when everything will be finalized, and improvements might be up to 30 rather than 14. So there is a lot changing in the yellow part of the bar that you've seen before, the species that are not yet published, but there are probably their category is final. And as you can see, deteriorations are concentrated in primates. Almost 30% of the primates has a worse conservation status now than 10 years ago, with a few improvements as well. For Idiota, again, the pangolins you see here, all the ones that were not threatened are threatened now, so there are a lot of deteriorations, and a lot of deteriorations in monotremes. Iroxes, well, it's not a special group. Horses, we had mixed stories in deteriorations and improvements. And that's a list of species. These are all the species whose status has improved since 2008. And Kevin was talking about the island fox this morning in the class. And the island fox had an incredible improvement in status from critically endangered, close to extinction, near to extinction, to near threatened, which is out of the threat categories, even if it is close to the threat categories. That's the only big conservation success that we can speak of. And then there are a few other species that have improved 2 categories, having moved from endangered to, again, near threatened, so out of the extinction risk categories, and a few others that have gone up, but not many. On the other hand, this list here presents only the species that have gone down by 3 or 2 categories, because including all that has deteriorated by just one category would be a very long list. And we have big losses among, if you go through the list, we have big losses among primates down here, and big losses in Australasian marsupials, mostly. And overall, this translates into a red list index that has gone down from, in the initial picture, mammoths were represented by just these 2 points. Now we have a third point, the one with corals, just to remind you, with corals going down very fast. This is what we knew between 1996 and 2008, and that's what we know now between 2008 and 2017. So the rate of decline of mammoths has increased in the last 10 years. They're going down, they're sliding towards extinction, and they're doing it faster than they did it in the previous decade. And this is really worrisome. The numeric changes in the red list index are small, but this means a lot of species, as you have seen, a lot of species going down and a few species going up. And of course, splitting the trend of the red list by orders, again, we see pangolins and primates and monotreme, where the monotremes somewhere here, yeah, going down more than the others. So these are the 3 groups that are driving the overall decline of mammoths in the past decade. The long-term trend for large mammoths tells a slightly different story. This is an update of the DiMarco et al. Paper that I showed you before that arrived until here, and until here we had sharp declines of both carnivores and ungulates. Carnivores do generally better than ungulates. They're more adaptable, they can tolerate some human disturbance. Ungulates are less less adaptable, and their red list index is always worse than that of carnivores. And that's a general trend, but if we look at the general trend is, I don't know, maybe it's even slowly, the rate of decline is slowing down a little bit, but this is composed by ungulates going down as fast as before and carnivores having even a slight improvement, so halting the rate of decline. So the picture that we had before was uniform for both, even if one was upper and one was lower, so that they were slowly going down together. Now they are taking the divergent paths, apparently. And then we have extinctions. We have extinction on the red list since 2008. Melomis rubicola was a very famous case, the first species extinction attributed to climate change. This species lived in a small cay in Australia, off the coast, close to the Barrier Reef. It was a tiny population that nobody really knows how it got there, and it was not enormously different from sister species in the mainland, but anyway, it was a good species. And that small population has been wiped out by extreme climate that has, at some point, waves have literally wiped the only habitat patch that was inhabited by the species. This is also possibly a species that will be rediscovered because there might be populations in Papua New Guinea. Papua New Guinea is not very well known and explored, so it might come up in the coming decades somewhere, but we don't really know. The only known population is gone. The other one is Christmas Island pipistrelle, again an island species, of course, that has gone extinct, has been declared extinct very recently. And then we have other species that are now extinct in the red list, but the situation is less clear than here. We don't know if they were extinct even before. Probably they were extinct even before, but they were not declared extinct. But these extinctions happened in the last decade. So why conservation is struggling so much? That's the point, that's the question. We know that conservation effort exists. That's the coverage of protected areas in terrestrial and marine environments. And the coverage of protected areas has increased since 1950 to almost 17%. The 17% Aichi target is going to be either hit or neared in 2020 for terrestrial environment, not as much for the marine environment. The target for the marine environment is 10%, and we're very far from it. And that's the coverage of different groups of species, and mammals are here, the green line. The percent of species meeting a decent conservation target of protection inside protected areas, and that's about 40% now. But the point is that protected areas cannot grow forever, and they cannot grow forever because the opportunity cost of protected areas actually increases non-linearly over time. That's the coverage of area protected, and that's the opportunity cost. So the more we protect areas, the more we enter into high-value areas that are costly to protect, and that poses a limit because we are so many and we need so much space for food. That's the big issue. So we cannot expand protected areas to whatever extremely large number without having really high costs for human societies. And the other point is that the proportion of species covered, of course, the number of species covered by increasing the cost, it tends to an asymptote at some point. So protected areas cannot do everything, cannot do the entire job. So protected areas cannot be the sole solution. And the other reason why protected areas cannot be the sole solution is that protected areas currently are doing a decent job at conserving, we said before, 40% of the mammals. That figure can be different in different analyses. But that is just taking into account the taxonomic dimension, so the different species. But this recent analysis that we did with Teresa Broom and others, that extremely luckily was published the same week as the paper with Kevin on PNAS, shows that the top priorities for conservation for species are not the same as for mammal phylogeny, and they're not the same as for mammal traits, and that the overlap between priorities for the conservation of mammal taxonomy, trait, or phylogeny is quite small. There are the green areas here. All three dimensions overlap here. The yellow areas represent the overlap of 2 of these 3 dimensions, and all the orange areas represent the absence of overlap. These areas are important just for one dimension, one of the 3. So these protected areas don't cover, if they do a decent job with taxonomy, they don't do a decent job with the rest, with phylogeny and functionality across mammals. And if you look at the overlap between the existing protected areas and the overlap priorities, the orange spots are the overlap priorities already protected. They are very few. So if you, when we complicate a little bit the problem to be solved, not just protect species A and B and C, but protect phylogenetic difference and functional diversity and so on, the problem becomes much less tractable, and we should protect basically not the entire world, but a large chunk of the world. And I don't want to enter here in the 50% debate, but it's really, we should protect a lot. The other problem why conservation is struggling is that certain threats that we thought as something for the future, either near or far future, but not for now, are actually happening now. This is a recent paper that we published. That's not just mammals, it's everything. It's all species, all levels of biodiversity. And it shows that biodiversity has been vastly impacted by climate change at all levels. There are observed impact of biodiversity at all possible different levels in different environments on organisms that are completely different. So this threat is happening, it is going on now, and its impact is happening now. And this is one of the reasons why all the short-term biodiversity projections that we made in 2014 look pretty green. Basically, I will summarize a slide which is a bit complex, but the slide, these are just representative indicators of anthropogenic pressures, biodiversity decline, ecosystem services, and conservation action. And the story that these indicators collectively tell is that conservation action is stepping up. There is more conservation spending, there are more international agreements, targets, the CBD, ITBES, and so on, all these nice good things, but still anthropogenic pressures are increasing and biodiversity is declining, and ecosystem services derived from biodiversity are declining too. So either this conservation action is not enough, which I believe is the case, or there is a certain time lag for conservation action to start actually having an effect on biodiversity. So given these overall situation and current status, what is the future for mammals? Now, to answer questions on the future, we start, of course, we exit from the typical ecological conservation science, and we have to enter a more shaky world, that is the world of scenarios. Trends, current trends, tell us something about what the world will look like in 2050. Human population, this is not from Malé, this is somewhere in China. That's a nice beach with a few people around. Human population is expected to hit almost 10 billion people in 2050. Temperature should be a couple of degrees more. It's very hard to tell, and it depends a little bit on the mitigation actions that will be taken, but that's likely that something will happen around 2 degrees. And actually 2 degrees is, 2 degrees not for 2050, but in general is the target now for most governments. So let's take it for granted that the temperature will increase at least a couple of degrees. And we expect by 2050 the loss of another almost 300 million hectares of tropical forest, which is more or less the size of India. So it's not a small amount. So we started making scenarios for what mammals will do in this situation. And the response of mammals, of course, is very hard to predict, because it depends at least on two things. How species will respond to the pressures, to the increasing pressures, and how, in the meanwhile, human societies will change. We are in the Anthropocene, and actually what we do is the most important thing in driving what will happen to the other species, as Michael Soule predicted long ago. So what are the options for the species, basically, in this burning, changing, and shaky world? The first best option is, well, they cope with changes in the environment. Certain species show resilience and adaptability. They can actually adapt. There is a limited space for evolution, even with rapid changes. They can shift range. They can try to move elsewhere in a place that is more hospitable for them. They can go extinct, local extinct or global extinct, if they can't cope in any of the other ways. So we started to think, can we predict which mammals will be more likely to be resilient, adaptable, and to cope with changes, and where will this happen? And we started working with we started working with climate change for for this topic. We could do similar analysis for land use change. We haven't done it yet. We started working with observed studies on the studies that observed effects of climate change. We did it on mammals and birds, but I will show you just mammals here. And we modeled these observed changes, which were basically categorized in negative changes, mixed, responsive, and even positive changes for some species that actually, with climate change, increased populations or expanded ranges. And we modeled this response as a function of the three components that the IPCC has identified as forming the risk of an impact of climate change. There are vulnerability, which is in a species, by a species point of view, is the specialization of species. And the variables that our model found were important were the diet breadth and fossoriality, whether species were fossorial or not. Exposure, how species are exposed to climate change, and our model found that seasonality of precipitations and minimum recorded altitude for the species within the geographic range were important variables to model exposure. And hazard, that is the intensity of climate change, that is the difference between current climate and projected climate. And based on that, we identified the groups that had more likely negative or positive changes. These are the observed negative positive changes, and the proportions are the proportion of species within the entire group that is expected to have a negative or positive change. So the species for which we had mixed responsive, at least some positive, some negative, and in this case, even more positive than negatives, were carnivores and rodents. So carnivores come up repeatedly as being adaptable in several ways. And we actually, based on our model and the life history traits of carnivore, we expect more positive responses than negative responses. Still, we expect 30% of the carnivores to respond negatively to climate change. But in other groups, and again, we have seen these groups elsewhere in this presentation, the response is expected to be constantly, consistently negative. Marsupial carnivores, kangaroos, koalas, wombats, primates, elephants, all these groups are already doing very bad. And they are all the species in these groups are expected to do even worse with climate change. So based on these results and looking at what is the proportion of threatened species within the groups, we estimated that it is possible that already 50% of the species that are now threatened have already been impacted, together with other impacts, with other anthropogenic impacts, have already been impacted by climate change, although we don't know it. No one has observed this impact. But their traits tell us that they are very similar to species that have been observed to be impacted by climate change. And this map shows where we expect the highest impacts from climate change. Unsurprisingly, Australia is one of the places because it contains all species that are 100% expected to respond negatively. And I would say all the southern hemisphere is expected to do worse than the northern hemisphere by looking at this picture. That's under the representative concentrations pathway 6.0, which is basically the closest to the business as usual that we can expect for the coming decades. We also tried to investigate which species are more likely to shift ranges, which ones can cope with change by moving away and finding a suitable climatic space elsewhere. And this is analysis that we published a few years ago with my colleague Piero Visconti. It's it's in the IPCC report on terrestrial and inland water systems, and it's again, this slide conveys much more information than the information that we provided actually, because it conveys also information on plants and other groups, not mammals, butterflies and so on. But basically, these are the expected velocities of climate change under different scenarios of emissions. And this is the trend scenario. What happens if we don't change policies, neither for the better or the worse? And what is the expected effect in mountain areas, in flat areas, and that's a global average. Of course, in flat areas, to find the same climate as 10 years before, if temperature increases everywhere, you have to move a lot more than in the mountains. So the climate velocity is much higher in flat areas and in mountainous areas. If you have a species that is found along a very steep slope, that species can move 100 meters up or down and find a different climate. But you have a species that is found in a flat land. If the species moves 100 meters up, down, well, then nothing changes. It has to move hundreds of kilometers. So that's why the speed is different. And just simply looking at the global average, you see that that's the dispersal distance that could be covered by primates, by rodents. We have carnivores here and ungulates, not even toothed ungulates, just split-toothed ungulates. And basically the only ones that have a chance to move fast enough are the ungulates. Even carnivores, the median for the carnivores is okay. It's better than it's enough to move by looking at to find climatic space by looking at the global average change, world average change. It's not fast. Wouldn't be fast enough in the pampas, for example. That's flat areas. That's how much they should move, and that's what we expect them to move. So and primates, of course, do horribly. They're very philopatric. They don't disperse. Rodents are too small to do decently. So most of the mammals actually wouldn't be able to move fast enough to find suitable climatic space elsewhere. And then there is there is the elephant in the room. That is what we are going to do, what humans will change in the world, and what can be the effect of these changes on biodiversity. And here the situation is slightly different. The picture is slightly less grim if we can do something really. We know that policies have an effect on biodiversity. We know that this is an example. This is the red list index of South American carnivores after CITES, the fur trade ban in 1975. And we see that after a time lag of a few years, the red list index of South American carnivores has gone up significantly from 0.7 to 0.8. That's much more than we have seen in all the pictures before. So that's a big improvement overall for the carnivores of South America. That's the opposite situation. That's not a policy, but a societal change. That's the collapse of the Soviet Union. The Soviet Union had strong regulations and strong enforcement of regulation. After the collapse of the Soviet Union, here, we see that the delta red list index has increased a lot, and the decline of species has increased its rate on the subsequent 2 decades, because after the fall of the Soviet Union, there's been a long period of more or less anarchy in the entire Western Europe and former Soviet Union, when everybody could do everything. There was no law and no law enforcement. And this was a terrible period for biodiversity in that part of the world. I do field work in Albania, and I still see the effects of what happened in the early 90s in Albania, that they destroyed entirely and large chunks of forest that are not recovering because there is nothing left, absolutely nothing left. I don't know how long it will take. So based on that, we know that societal decisions, societal changes can have an effect, a big effect on biodiversity, a good effect or a bad effect. So we decided to explore what are these effects. And to do that, we built a scenario model that we applied mostly to mammals, but for example, my colleague Piero Visconti is applying it to birds as well. This model is called InSights, that is Integrated Scenarios of Global Habitat for Terrestrial Species. And the logic of the model is that we use scenarios of socio-economic drivers that are not produced by us, of course. They are produced by groups that do integrated assessment models, and they have a lot of outputs. The output that is most important to us are maps of scenarios of land cover change that are coupled with scenarios of climate change. So in different climate scenarios, we have coupled scenarios of land cover change. And these groups play a lot with different policies to, for example, different policies to achieve the same level of climate mitigation and so on. So we can use them to explore the effects on mammals. And the logic is that we use climate to project the bioclimatic envelope within which the species can live. We use the current range to estimate the bioclimatic envelope in which species live now, and we project that into the future based on different assumptions on dispersal. Either assumption 0 is that species don't disperse, but they don't have any direct effect of climate, so they only respond to land use change within the range, or they go locally extinct where climate becomes unsuitable but cannot expand the range, or they can do both. These are the three assumptions that we are currently using. Of course, we can build different assumptions in the model. And then within projected climate, let's say that this is current climate and we estimate the bioclimatic space based on this, we project it based on projections of climate change. We use suitability models for based on land cover categories to project suitable habitat. It doesn't show up very well in this picture in particular, but it should be more colored. Suitable habitat for the species without these projected ranges. So these are our projections of where mammals will be in the future. And how much these ranges can change depends also on the capacity of the capability of species to disperse. And we applied these models on a variety of projections of land use change to answer a variety of questions, and we're still doing it with many species, and also to a variety of scenarios of climate change. I will not get into the details of this. But I just want to show you a few of the results. We explored, for example, the effect of a change in consumption patterns by our societies on the availability of habitat for mammals. This analysis in particular that I will show you, the first one is at the European level. And the scenarios are a business as usual scenario, so no new policies, a continuing expansion of agricultural, fisheries, aquaculture, increased use of fossil energy, water products, and so on, associated with its climate scenario. This consumption change scenario is basically a scenario that achieves the SDGs, the Sustainable Development Goals, and it does so by reducing meat consumption. That's interesting because meat consumption in the scenario is reduced, and I'm touching a sensitive issue here in Argentina, but it's reduced to 25% of the current level, and it is still twice the amount that is recommended for a healthy diet by the World Health Organization. And the US also would be a sensitive issue as well. So 1/4 of the meat we eat now would be still too much. But anyway, let's not think about it. And let's think about what are the effects of these and the effect of reducing waste and use more reduced impact logging. This is the effect for European mammals. That's the amount of available habitat as compared to year 2000 for 5 decades until 2050. The business as usual scenarios that you see here with different assumptions of dispersal. So you have here the assumption in which species just go locally extinct and don't disperse. That's a worst case scenario when climate changes and land use changes. This is and the intermediate case in which species respond to climate change with local extinctions and local colonizations, and the best one is the scenario in which species don't respond at all to climate change, they only respond to land use change. And that's the same for the blue lines. But the difference is clear between the blue lines and the red lines. In the best case scenario with the blue lines, the amount of habitat available to large mammals in Europe remains constant for the next 50 years, while with the best case scenario for no change in consumption patterns, business as usual, it's mammals are expected to lose about 7% of their habitat. With changing assumptions, the situation worsens to losing more than 20% of the current habitat in the business as usual, as opposed to losing a little more than 7, 8, 9% in the business as usual. So there is a clear difference between policies. Policies make a markedly different outcome in terms of availability of habitat for mammals, because it makes a difference on how we use land, basically, and how much we impact on climate. And this is a global result based on the Red List Index for the same group of species, large mammals. And you can see, again, different assumptions of dispersal, ABC. The blue lines are consumption change. The Red List Index remains constant or goes up. The red lines are business as usual, and the Red List Index goes down as compared to today. So species continue to decline. We also tested the effect of alternative strategies to mitigate climate. We are doing this right now, actually. We are using another model of land use change, and in that case, the land use change is different ways of remaining on a representative concentration pathway 2.6, which is the best case scenario for climate change. And we compare it to a business as usual again. But the climate mitigation can be done through the widespread use of biofuel, or it can be done through passive and active restoration of forest. But both achieve the same climate pathway. And of course, this is an obvious result. Afforestation is very good and actually would increase the amount of habitat available to mammals. The interesting thing that we are exploring right now more in depth is that actually the use of biofuels would be worse for mammals than business as usual. So for mammals, it would be better to have worse climate change than climate mitigation done with biofuel. And that's something that is recurring in several analyses that we are doing right now. So in terms of habitat for mammals and mammal distributions, climate change is not necessarily as bad as certain climate mitigation strategies. And that's the same result split for carnivores and ungulates. And again, as usual, carnivores do better than ungulates, but the pattern is the same. So finally, I just wanted to show you a couple of slides on something that is related. We haven't yet applied the full insights framework in this case, but we're also working on scenarios for invasive species. We are using the ranges that Team Blackburn has collected for invasive mammals worldwide. There are 255 species of invasive mammals worldwide, and basically the same type of species distribution models that we've done in the past in the native range of the species. In this case, were applied to the native range plus the introduction range of the species. And this map shows the current potential for mammal invasions. if mammoths were released elsewhere, and you can see, wow, parts of Argentina are a hot spot of potential for invasion. That means that climate, in this case, the analysis is just climate. There is no land use yet in the analysis. We will incorporate it in the analysis. We're doing it right now, actually. But people in my lab is doing it right now. But for now, what we can tell about climate is that there are certain spots that are in Argentina, notably Mexico, and Australia that are particularly prone to invasion. They are suitable for a lot of invasive mammoths. So if more invasive mammoths were released in those areas, they would have a high chance to succeed, at least in terms of climate suitability. Of course, that's not the only factor for a successful invasion, but that's one important factor. And the reason why we get this result is that actually most species, most invasive species are from temperate cold areas, not from the tropics. So the most invasible areas are the temperate cold areas. Again, if we look at the difference between now and the future, that's a difference with low climate change, and that's a difference for comparison with high climate change. And you can see that with low climate change, we expect that the invasion potential increases more. If you look at Argentina again, which is a good example, with low climate change, invasion potential in the future increases more than with high climate change. And again, this is because most invasive species are from relatively cold areas. So a very high climate change actually has a negative interaction with invasion potential. If temperature increases a lot, there is less climatic space for the species that are currently invasors. Of course, we don't know anything about potential tropical invasors that cannot invade right now, and in a tropicalized world could become invaders. We are also working on that, but it's too much, and I don't have results to show you right now. But that's for currently invasive species. And that's it. That's all I wanted to tell you for this plenary. I just wanted to say a huge thank to my lab, the Global Mammal Assessment Lab in Rome, that is doing a lot of wonderful analysis, and to the REDLIST partnership that is producing a lot of the big baseline background data that we use in our elaboration. Thank you very much.